Frost protection for strawberries. Critical temperatures of strawberries are based on the stage of bud development. At the tight bud stage, about 22 degrees is considered the point at which damage will begin to occur. As we progress to the popcorn stage, 28 degrees, open blossoms, 30 degrees, and then with fruit, about 28 degrees again. Several variables can affect the actual critical temperature for a plant and the amount of injury received. Things like soil type and condition have an impact. Moist, dark soils hold more heat than dry, light-colored soils. Some cultivars bloom earlier than others and are therefore more prone to spring frost damage. As we just saw, the stage of bud development will have an impact on how much cold the plant can tolerate. And weather conditions leading up to the cold event also have an impact. If it gets progressively colder leading up to that cold event, you'll actually build an ability to tolerate more cold than you would have if it was fairly warm with a sudden drop in temperature. The severity of the cold, how cold did it get, and how long did it stay cold are also factors. You can have both radiation frost and advective freezes in an area. Fortunately for us, radiation frost are more common. They're characterized by being relatively localized, that is, affecting a relatively small area. Winds are either non existent or calm, less than 5 miles an hour. Skies will be clear. The cold air mass over the Earth will be relatively shallow, and the inversion layer will develop. Within the inversion, the air closer to the ground is actually cooler than the air above it, which is directly opposite of the way you would normally see it. The good thing about a radiation frost event is successful frost protection is a possibility. On the other hand, advective freezes occur over large areas, possibly more than one state or an entire region of the country, as we saw back in 2007. The winds are going to be high, in excess of 5 miles an hour. You may have clouds or may not. The cold air mass over the earth is going to be fairly deep, and there will be no inversion layer. Unfortunately, with advective freezes, our ability to protect the crop is very limited. There are both passive and active frost controls. Passive controls include things that may be difficult or impossible to change once put into place. Site selection is a prime example. How high is your site in compared to the surrounding area? In a radiation frost event, an elevated site has some natural frost protection. Likewise, what is the aspect or direction of slope? That can impact the frost susceptibility of the area. Many passive controls are good horticultural practices from other standpoints. A good example is air drainage. If you have good air drainage, you've got a certain measure of frost protection, but you also have a certain level of disease protection. Good ground cover management, both in and around the planting, will also help with frost control. Passive controls tend to be relatively inexpensive when compared to active controls. Active controls are supplemental to passive. They are costly and they all have definite limitations. For example, if you have irrigation for frost protection and there's a lot of wind, the wind can distort sprinkler discharge patterns so your coverage is poor. It can also increase evaporative cooling, making irrigation not feasible to use. If you looked at wind machines for frost protection, in an advective freeze there is no inversion layer and therefore wind machines are not effective at all. Irrigation is commonly used for frost protection in strawberries, and it works because as water freezes, it gives up heat, and as long as you're continually building more ice on the plant, the temperature of the ice and the plant will remain at 32 degrees Fahrenheit, which, as you recall, is above the critical temperature for crop damage. Stopping the irrigation before active melting begins can result in evaporative cooling, lowering the temperature of the ice in the plant below air temperature to the point that you could cause more damage than if you never used irrigation at all. Under favorable conditions, irrigation may actually protect down into the mid-20s. Rules of thumb for irrigation involves things like the minimum water application rate. It's suggested that 1/10 of an inch to 1/1500th of an inch of water per acre per hour is used, and that figures out to 2,700 to 4,100 gallons of water per acre per hour. This means you need to have a sufficient water source to allow you to irrigate for 2 or 3 consecutive nights for several hours per night. And the irrigation system itself, smaller diameter nozzles are suggested. Closing up the sprinkler spacing and staggering them, 30 by 30 spacing is suggested, to the point that you have no area of the field that's left unirrigated. Metal sprinklers tend to be better as far as minimizing icing, and have a sprinkler head rotation rate of at least once per minute so that the ice does not have a chance to dry before the sprinkler head re-wets it. When do you start irrigating? First of all, monitor the temperatures in the lowest part of the field that you want to protect. Put thermometers in the aisles at the level of the flowers in that low area. Look at the dew point of the atmosphere. The dew point is the temperature below which water droplets begin to condense and dew can form. And this will vary with pressure and humidity. A high dew point, high humidity means that you can wait longer to start the irrigation system. For example, a dew point of 30 degrees Fahrenheit, the suggested starting air temperature for irrigation is about 32 degrees. However, with a dew point of 25 degrees Fahrenheit, it's suggested that the irrigation system be started at about 35 degrees Fahrenheit. When do you turn off the water? As I said earlier, once you start to irrigate, continue until active melting begins. Do not shut the water off until the sun comes out and the ice begins to slough off the plants, or until you observe active melting occurring. Wind can have an effect on overhead irrigation for frost protection. Under windy conditions, heat is lost at a faster rate, therefore more water needs to be applied. However, with a very slight wind, there is actually less chance of flower temperatures falling below air temperatures because that wind will mix the air at the boundary of the flowers. So the bottom line is a mild wind, say 2 miles an hour or so, can be beneficial if temperatures stay above the critical point, but they'll be detrimental when temperatures approach or drop below that critical point. Under extremely windy conditions, irrigation is not recommended because heat loss to evaporation can be greater than the heat released from freezing water, in addition to the wind disturbing sprinkler patterns giving you poor coverage. Row covers are used in strawberry production for several things. In the fall of the year, we use them to promote branch crown development. In winter and spring, we use them to protect for cold and wind at the winter and frost and freeze protection in the spring. And then we also use them to advance flowering and early harvest in the spring. Row covers provide a physical barrier to heat loss from around the plants. The plant temperature under that cover may eventually drop to the same level as that of the air outside of the cover, but it'll take longer for that to happen. Row covers do not provide additional degrees of protection, but they do buy time since temperatures fall less quickly. Maybe slowly enough that a supplemental practice like irrigation is going to be unnecessary, or if it is needed, the less water could be used to get the same degree of frost protection. Also recall that 2 layers of a lightweight row cover will actually provide more protection from cold than 1 layer of a heavier cover. Irrigation can be used in addition to row covers, so water can be applied directly over the row cover to protect the flowers underneath. It's essential to know the temperature under those row covers to know when you want to start the irrigation system. So irrigation plus row covers is the one technique that may actually provide some protection during an advective freeze.